All right, so let me get going today. First, what I want to do is just one more question, math test review of one of the more complex varieties. So let's see if I can get this to right for me. All right, so we've got a function here that maybe you can tell by looking at this is a whole bunch of chain rules necessary. Again, look at the overall structure. I've got an arctangent on the outside. This one with lots of parentheses is easiest to identify that way. It's an arctangent of a log function that's raised to the 8th power. So if I'm evaluating this, I raise to the 8th power and then find arctangent. So we can deal with the derivatives of all of those pieces in whatever order we want. I'll work, let's see, outside in. So if we had y equals, I'll call it something else, fx equals arctangent of x. We know that the derivative of that one is over 1 plus squared. Arctangent of x, I have arctangent of this. I mean, in terms of the first step for writing our derivative, I'd want to have, if we're working outside in, I'd have 1 over 1 plus all of that's the argument of the arctangent function squared. So I have log base 5 of x to the 8th power squared. No, you could write then to the 16th power if you want, instead of writing 8th power squared. But this would be without any extra algebra simplification. And now let's deal with the fact that we haven't talked about what this is inside. So kind of done part, let's focus on the rest of this, which is a log base 5 of x to the 8th power. Well, so the next working in is 8th power to deal with. If I have a function that's raised to the 8th power, it's going to be 8 times that same function to the 7th power as its derivative in part, and we have to deal with chain rule, but deal with the 8th power aspect, 8 times log base 5x to the 7th power is working inward. So we've dealt with 8th power. Now we're at base 5 of x. So the derivative of a logarithm function, natural log is the easiest. But if I had gx equals log base 5 of x, it's actually what we have here. It's not log base 5 of something else, it's the innermost function. The derivative of this, remember, is still a 1 over, it's just got an extra factor in the denominator to account for the base of the logarithm, over x times the natural log of 5. In both, keep in mind that the derivative of logarithmic and exponential functions with bases other than you have natural logs of numbers to put onto them, not natural log of x. The x's in other positions. So this is the last piece of our function here. So 1 over x times the natural log of 5. And again, you could have started maybe from that, say, oh, x log of 5, and then with an 8th power of that. When I see nested chain rule sorts of function, like a function of a function of a function, I find it easiest to work from the outside in so that I don't only replace the inner function with its derivative. So notice that this isn't 1 over thing with x natural log of 5 raised to any powers. When I have something raised to a power, the derivative of that lower power. But it's of the same item. So x to the 8th derivative, if that had been something we had, is 8x to the 7th. It's not 8, it's something else to the 7th. That same inner function is left intact. All right, so that's all of this question. Let me clear this off. And let's look at something else that I showed you on, let's see, what is that? Tuesday. So, picture away so I can get this. So function r of f of x gives a rated function f of x that has f of 1 is -7, and here's the rule for r of f of x. So on Tuesday, I talked about a couple of applications where there's a whole story that went along with it. This is the generic I showed you at the end of it and said, see if you can figure out this is the generic, work on it on your own sort of question. Well, haven't actually asked the question yet, but if I wanted to write a rule for f of x based on this information, I could do this in OpenForm. So OpenForm is just meaning don't worry about the computations, express what needs to happen. This is the rate at which f changes. I know I can recreate the net accumulated change due to this rate by integrating, right? We can form accumulation by integrating a rate function. I'm just going to write it symbolically, r sub f of something. I want to write a function f of x, so I'll use x inside the integral. And then there's the rest of this that we have to talk about. So where does it start? 0? Well, remember that this just measures the accumulation or the net change. I need to know the overall total value. I also have to start from someplace. Just like if you have an equation of a line and you don't have the vertical intercept, if you have some other point, you use point slope form to write it. That's what we're doing here. We're going to do a y initial plus dx. So I'll write it like that for now. So this is kind of an informal, this is along the lines of what we want to do. Initial plus the sum of all our mvx's. So this is the idea of what we want to write. Putting in the details, including this number, actual expressions there, I could say that f is given by y initial. The initial y value that we have isn't at independent value of 0, it's an independent x value of 4.1, but here we go, that initial value is -7 plus whatever happens after we have 7. So these, remember, are our x values here. X, we let t take on all the x values between beginning and the end. Well, the beginning is wherever we want it to be. Here's where we know the x value that corresponds to -7. So I'm going to start accumulating after 4.1 up through any value of x. And I'd have this then, 14 cosine of 7t plus 3, writing in the actual rate function, dt. So my fx function in OpenForm, I have my y initial plus mdx structure, or my starting value plus accumulation due to this rate starting at that point and moving on. So I have t take on all the values from x equals 4.1 as far as I want, and that gives me a function of x. So let's look at another question that I posed for this one. What do you know about the closed form of f? Meaning, without having this crazy integral in here, how else could I write that? Well, what sort of function is, can you write it in closed form? So if I wanted to know a little bit more about this, say, well, this is the rate of change of something. So just thinking about this, this is the rate of change of function f, or I could even think this is, oh, sorry about that. Get this back to drawing properly. So if this is the derivative f prime of x, can you imagine what f must have had in it? Well, f of x would have to have something where I take a derivative of it and it turns into a cosine function. Oh. Well, the derivative of a sine function is a cosine function. So just kind of thinking about what I would need to do in order to get that, it'd have to be something like this. And if I take a derivative of sine of x with cosine of x, if I take a derivative and I want it to end up cosine of 7x plus 3, I better have had sine of 7x plus 3 as a part of this. So here's a function kind of on the path to becoming this. All right, so what if I took the derivative of this function f? It's not, but it's pretty close. Sine of 7x plus 3, derivative would be cosine of 7x plus 3 times 7. Well, that's not what I want. I want 14. So guess what I'm going to do? I'm going to throw in an extra 2, which would just carry through. That times 7, I end up precisely this. One problem though, this isn't exactly what we want. If you can think about why not. There we go. This right here meets this qualification. It has the right rate of change. I doubt very seriously that f of 4.1 in this function would turn out to be negative 7. But I know generally how this works. I know that this expression, based on fundamental theorem of calculus, remember we had this, was a generic sort of expression. I'll write it r sub f of x dx from a to b. Remember we could rewrite one of the forms we talked about. This would be f of b minus f of a, or if you had it here instead of b, thing, doesn't matter what the symbols are. If you had an x up here, you better not have them there. But this expression, this is r sub f of t. I need the r sub f of t from a to b, or from 4.1 to x, should be the same as f, which we just came up with an expression for f, something that has this rate of change, to 7x plus 3, evaluated at x, so as I just said, and then evaluated at 4.1. All right, so I want r sub f of e dt, so that I get f of x and f of 4.1. So, but I'm just going to use this f here. So this expression, this is my f that I came up with, something that has the proper rate of change. All I have to do is come up with something, and this will work. Because the fundamental theorem of calculus didn't say anything about, well, what about initial values? It says that due to this rate, I can measure the net change by finding something that has that rate and subtracting. So let's use this. I'll use, so that of x equivalent, we're going to use, it'd be this 14, not 14, 2. Looking online. So I have this 2 sine of 7x plus 3, and the f of 4.1 in terms of x minus f of 4.1. These two expressions here are what I need. I'm not going to write the symbols. I'm going to write the expressions with this sine function here. Would be 2 sine of 7 times 4.1 plus 3. I'll write that so it doesn't look like a decimal. 7 times 4.1 plus 3. All right, so these two expressions subtracted, top one minus the bottom one, are equivalent to this, according to what we had. So the name of this actual function was f of x. So this is my fake f of x. It's just something that has the same derivative as real f of x. So a real f of x, like I said, it's not quite this because this doesn't meet the property. But this expression minus that one is the same as this integral. So if I do negative 7 y initial plus the equivalent due to fundamental theorem of calculus of this expression, I'm going to have, let's see, 2 sine of 7x plus 3 minus 2 sine of, what would that be, 27 plus 3, otherwise known as 31.7. But taking a look at this, you can see, oh, well, yeah, if I put in x equals 4.1, this term and that term are identical. They subtract one another off because this subtraction sign, I'm left with this -7. So it takes care of the initial value doesn't match, or this gives us the right, the right vertical intercept, the right vertical shift for a function that has two properties. You have to have its rate of change and all right, so and let's just stop at that. Let's get back to what we need to do other topic-wise. So we were talking about the end of last class, first and second derivatives, and how those are related to graph shapes. So there's a couple of, well, there's a word and some variations on that word. Critical values is something that I want us to talk about. So the meaning of the word critical value, it means we're talking about a value of x where f of x exists, meaning it's x is in the domain, f of x exists, and the derivative is 0 or the derivative doesn't exist. So these are kind of bizarre points in our graph's shape, but they're also things that algebraically we can solve for. So thinking what we were talking about on Tuesday, if I'm looking for a point where a function exists and its derivative is 0, its derivative has a value of 0, its rate of change is 0, not a positive number indicating function increasing or a negative number indicating function, but 0. That would mean is locally approximately remaining constant, or approximately like a horizontal line, and it's been really close to that particular x value where the derivative is 0. Now, a derivative doesn't exist, can look like a variety of things, but one of the things it might look like is a sharp point, like the corner of a y equals absolute value of x graph. It could also just look like a vertical section in a graph, but these can look different from a distance also. But what this looks like is we don't have a rate of change. If you zoom in closer and closer, the function, the ratio dy to dx changes in y to changes in x becomes something we can't compute. So if I have a derivative equal to 0, let's go back to the easier case. Why this might be critical for us, helping us optimize something. We talked briefly like lower costs or higher returns or better volume outcomes. But if I have a derivative that's 0, like I said, locally rate of change 0, that means that maybe to just kind of think about what this looks like as the graph is generating from left to right, that our function stops or pauses momentarily from either increasing or decreasing. It was increasing and then it paused from that, or it was decreasing and it paused from that. So let's take a look at what this might look like. How there's a few different scenarios, a few different ways that a graph could look if its derivative is 0 at a point x equal to c. So I could have what's called a local maximum. So something like this. If this is my graph f, graph of the relationship f, as I go from left to right here, I can see, oh, well, as x increases, y increases, and then pauses, and then decreases. So it stops going up and then moves to going down. Not suddenly, there's this kind of pause here. Or if you can imagine like generating this graph on GC, watch the height of the arrow goes up, kind of pauses for a second right at the top before it starts dropping back down again. So this is a situation that's called a local maximum. Now, let's think about what's happening with the rate of change function then. So rate of change function, we said, oh, well, this function is increasing and then pausing and then decreasing. So its derivative would then be, as we were talking about yesterday, positive, corresponding with the increasing function graph, a rate of change of 0, right at that maximum, and then our rate turns negative after that. So I've got a function whose pattern is the function values increasing, then pausing to turn around and decrease. We've got a rate of change function whose value is positive and then turn to 0 and then negative. So looking at what that graph would look like. If I'm looking at a rate graph, it has a positive value, then hits 0, and then becomes negative. I don't know necessarily exactly what shape it would have, but one possibility, just kind of something that's positive, hits 0 at that spot, and then is negative, well, somehow or another going downhill. So that means that this whole derivative graph is decreasing, or the values of the derivative are decreasing throughout. Remember, we talked about that yesterday. A high positive number to a lower positive number to 0 to lowish negatives, as in close to 0, and then farther from 0 negatives, more negative. This is a sequence of decreasing values of a derivative, something continually going downhill. So our second derivative, the rate of change of the first derivative, think about, well, how do I describe the derivative of this? It's always decreasing. So therefore, its second derivative is always, I don't know necessarily that it's a constant negative. I don't know a lot of details about it, but it would have to only have negative values. Maybe it's higher one place and lower other places, but something that has all negative values if I were graphing second derivative. So let's take a look at another option, because this doesn't have to be the pattern that we have. We could have a local max if our first derivative is 0. We could have a local minimum, meaning by local, I just mean not looking at the entirety of a function. There could be other stuff going on in other places, but just looking at a small neighborhood around x equals c, a small moment around x equals c to see what the pattern is immediately around. So if I have a local minimum, so sort of picture from above, see if you can do what we did in the previous example. If you're watching this on tape, pause it. I'll wait for a moment. If we have this situation upside down. So thinking about what happens with my graph. My original f, what the pattern of the values are there, what happens to its derivative, and then the derivative of the derivative. You can maybe see here that I've got, oh, well, this was increasing, pause, decrease. Watch the arrow. Increase, pause, increase. No, it doesn't actually stop at the bottom, but just the changes in the values are so slight. And left to right, you can see this is moving consistently. The x value is increasing at a constant rate of time. So in the same amount of time, hardly anything's happening to the y values right near that vertex of the parabola. So I've got x value decreasing, or y values decreasing, then pausing, and then increasing, which means that the derivative values are negative, then 0, and then positive. So if I were going to sketch a graph of that derivative, it'd be kind of the reverse. Like, oh, well, I'd have to have something with negative values that hit 0, continues on positive. Maybe it's a straight line, maybe it's not. Just draw it kind of as a straight line. If this is a straight line, it's certainly a straight line with a positive slope, or this graph is increasing all along. So if I'm thinking about the second derivative or the derivative of this first derivative, then I've got something that has all positive values, whether it's actually constant at one positive value or vary through a few, depends on a lot of precise information about what this graph is over here. It looks like a parabola, but it's really just part of something. All right, so I'm going to clear that off. And there we go. So the thing to point out here is that these are two examples of what could happen if I have a first derivative whose value is 0 at a specific spot x equals c. But there are two more options, thinking about combinations of things that could happen. This went from increase to pause to decrease. What if it didn't decrease? What if it increased again? That's an option. Or this from decrease to pause to increase. It doesn't have to change to increase just because there's this pause or this 0. It can continue on the same direction it went. So I'll call this a rest stop or like a plateau sort of situation. If it increased, then pause, then increase. This is not a local max or min. It's just a plateau. It's a little flat resting spot in the graph, which would mean if you see this pattern of function values, the derivative isn't going to have this same look as before. Increasing function means positive derivative. So I've got positive, then 0, but then positive again. Or if I were going to see what this derivative looks like, I'd have something with positive values, but it has to go through 0 and then be positive again. So maybe it looks kind of like that. It have to be something that goes down and back up so that I have something that's a positive value, but then have something that's 0 and then have positive again. It must go down and back up as a derivative. And this is a shape that looks familiar from our last graphs. We're thinking, well, what's the second derivative look like? Well, this is decreasing, hits 0, or stops decreasing and starts increasing again right afterwards. So decreasing, pause, increasing. Oh, well, I know what the derivative of that looks like. Something's decreasing, it has a second derivative that's negative. When we get to C, I have a second derivative, rate of change of this, that's 0. And then this graph is increasing, so its derivative is something positive. Whether it's a straight line or not is up to things that we don't know just by looking at this. But just in terms of, this is the same sorts of patterns we saw last time. But just this time, the middle graph happens to be the one that looks kind of parabola-ish. Again, if we're just trying to analyze what's going on at this critical value, if you see this pattern of function values, or this pattern of first derivative values, or a second derivative that changes signs, like this, from negative to positive, all of these indicate the same thing. So what we're doing is working on analyzing, based on derivative values and patterns of derivative values, what's going on with the function without having to graph the whole thing. So just the other direction. Obviously, if this is decreasing and then pauses to decrease some more, then I've got, again, this, I've got negative derivative values, and then 0, and then negative again. So drawing wise, I've got to have something that's negative, hits 0, and then becomes negative again. So I'm going to have a parabola kind of like this, pretend that goes through 0. Not necessarily a parabola, but just something that's probably curved downward as opposed to straight lines, because this is very curvy. But again, this function is increasing and then pauses and then decreases, which means its derivative is positive, then hits 0, and then turns negative. The derivative of this function would look like that. The derivative of this function looks like that. So just putting in words what I'd said. It's the same patterns, but again, key point here is, the derivative of a function equaling 0 just on its own doesn't tell us much of anything. We need to know the patterns of what's going on. Get out of this for a minute. No, it won't let me. So I'm just going to click through this fast because it won't let me skip it. But I do want us to take a look at one particular polynomial. Now, granted, we have graphing calculators and means to do this, but the purpose in doing this isn't necessarily for dealing with simple functions that we can guess what they look like. It's for those that we don't really know, and specifically those where we don't know, and we also don't know the scale of where we're supposed to be looking. So that looking at a graph, if you're not sure the scale of how the changes are happening and where things are happening, it's very easy to overlook things. Now, polynomials, you probably know a lot about this polynomial from algebra classes. The 4th degree polynomial, so both ends go, since this is a positive lead coefficient, both ends go up, goes through 0, 3, and because there's a lot of terms, it wiggles around. So if I were going to take a guess at what this looks like, I'd say it probably looks like this. Since it's the 4th degree, it can go down, up, 4 different directions. This, you want to say that? So I'd say, it probably looks something like that. If we want to be more specific, we can look at patterns in the derivative. So just, let me clear off this silly scribble here. Think about this. If I want to look at, I can find values of this function, and you can do this on a calculator. You can use GC, you can use a handheld graphing calculator, but what I want you to do is take a look at the values of g of x at these different points, the values of the derivative, which is this function, cubic function, at those same points, and the values of the second derivative, which I don't know if I wrote that down on here or not. Yep, I did. Which those are easy enough to find. No tricky derivative rules for that. But take a look at the pattern of values that go with these. And I'm going to show them here in just a moment. We're going to look at what the patterns in the function values, what the patterns in the first derivative values, and what the patterns in the second derivative values each tell us about the function. And each one can tell us more than about the others. So here we go. So I just picked some points, 0, 1/2, 1, 1.5, 2, and 3. Well, 2.5 didn't quite fit on. But I can see in this, okay, g of x has a value of 3, then it goes down, and then it goes up, 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 up. So if all I had was just this, just the y values, or trying to sketch a graph of it, I might say, all right, so it goes down as low as 1.3 and then go up. So it looks kind of like this. Maybe that's part of the graph, maybe it's accurate, maybe it's not. And I'm thinking that this is the bottom of a curve. Well, I know from this, I'm probably right, but if I combine it with that, I can tell more. So looking at this, just, okay, this is the lowest number that I happen to have in this chart. At that spot, the first derivative is 0. Great, first derivative is 0. That means I've got a flat spot here. Now, I can also see my graph was higher on both sides, not immediately next to, but a fairly small neighborhood. That makes this low spot at x equals 1.313, or x equals 0.5 rather, and y equals 1.313 as a low spot on the curve. That seems right. Now this second derivative of 9, key fact is it's positive. Second derivative of 9 would indicate that this function turns upward at that same point. So it's turning upward, pausing, in terms of it's not going up or down, it's curving upward, and the y value happens to be 1.3. Those three facts put together tell us that the shape like this, and that at x equals 0.5, here's the y value, that is actually the bottom of this hill. This is a local minimum. Now, there could be lots of other stuff going on in the graph. I don't see any points within that here. Doesn't indicate that there aren't, because I don't have a single x value. I just have some x values. But taking a look at the pattern in the first derivative, I see negative, 0, positive, 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 0 again, and then 10. So here's the spot where my curve is pausing based on the closest pieces of data I have around it. Without doing additional computations, I can see the function was increasing, since this is positive, and then pauses, and it seems to be increasing again. So around x equals 2, my graph is going essentially horizontal, goes through the point 2,3. And so just as a separate picture, just modeling what's going on around 2,3, say, oh, well, it's going essentially horizontal, and it's also not curved up or curved down. It was increasing and then pauses and then increases again. So maybe something like this. Now, I didn't draw this particularly horizontal because I'm not great with this pen. But there we go, maybe around the point 2,3, I was doing something like that. So when the first derivative is 0 here, it happened to be a minimum. You can tell kind of from this, and also from the fact that this is positive. The second can tell us about curvature of the original graph. Well, our curvature here is turned up, here is turned up, here's a mystery. Here is turned down, here is turned up. If our graph is changing from turned down to turn up, or concave down to concave up, this is that inflection point we were talking about before, last class, where the curvature changes. A inflection point, and it's not curved up or curved down, it's changing from one to the other. Just like at this point, our graph isn't increasing or decreasing, it's changing from one to the other. So you can either, when you have a 0 value, depending on what happens, you can change one sign to the other, or you can go back to where you were. So having a value of 0 doesn't tell you what's happened, you have to know the around. This I see is a change point. I'm changing from downhill to uphill. So this 0 is a minimum. This I'm changing from uphill to uphill. Oh, that's not changing. This is just a flat spot. And mixed with this, I can see my second derivative was changing at this point from curved down to curved up. So I can verify that matches. These two put together can tell me that's an inflection point at x equals 2. So if I want to look at a graph of this function in GC, I could verify that all of this kind of matches. Now, here's another 0, kind of interesting. Here's this 0. Looking at this, the second derivative is 0, while the first derivative is positive, and the y value is 2. Okay, well, y value is 2 is just the position on the graph. I've got a point, let's say that this is my point 1, 2. The first derivative is positive. My graph's going uphill through there. But my second derivative is 0. Let's look at what's happening. Well, it was turned up, and then hit 0, and then turned down. So at this point, 1, 2, my graph is changing from turned up to turned down. It didn't have to be flat in order for the curvature to change. I can have any first derivative view and have my second derivative be 0 with a curvature change. So my function from here, this function decreases and then increases, and that's all I can really tell. looking at first derivative, I can see it decreases, goes uphill, flattens for a second, and then continues uphill. My second derivative, I can tell it's curved up, flattens, and then changes to being curved down. Ooh, sorry, lost my interconnectivity for a second. So it turns up, curves up, flattens for a second, so it's not curved up or down, turns to curved down, and then turns back to curved up. So you can tell a lot more about this from here. Well, let me see if I can put this in GC really fast. I didn't do this in advance, I apologize. But let's see. Share something else instead. All right, so in GC, let's see, there we go. I want to put, let's see. If I can get to the right function. Hold on for just a second. I hope you're seeing this, graphing calculator. Just trying to make sure this is showing for you. All right, so I want to put in, let me define my function first. X and control 9. There we go. Equals x to the 4th minus 6x cubed plus 12x squared minus 8x plus 3. So I want to graph y equals f of x and look at the same portion we were looking at. I'm just going to look at, let's see, -5 through 4. So we don't have a lot of excess information. Now, and I'll zoom this out horizontally. There we go. So what we were talking about was, let's see, here's our, let's see, we had 0.5 through 3 approximately. Let me zoom back in a little bit. It's a little bit too spread out to see. So we've got around x to the 4th. Did I get the right function in there? Or am I missing a number? X to the 4th, x cubed, 12 minus 8 plus 3. All right. So around 0.5, we have our value 1 point, whatever it was, 313 or so. And that was our minimum. We had our function decreasing, then increasing. Negative first derivative changes to 0, changes to positive. And then around x equals 2, we also had a 0 derivative with a increasing pause increase to the right of that. And in terms of our second derivative, it was like -24 and then positive 24 and positive 9 and some other values. And right around x equals 1, we saw it was 0, and it changed from positive to the left of that to negative on the right with a derivative of 2 right here. So we're going uphill, but the curvature is changing. And our curvature remains negative, second derivative negative, curved down until we get to x equals 2, where the second derivative is 0, and then it's positive afterwards. So left to right on this graph, let me write on this. So thinking about first derivative sorts of stuff, just starting at 0 through 3, which is what we had before. So between 0 and 0.5, my function is decreasing, which means it's, oh yeah, I got F here. Sorry, it's G on the screen. F prime was negative. And from this point to, well, the rest of the graph, F is increasing. With a slight pause here where it stops increasing for just a moment, which means that my first derivative is positive, first derivative positive. We've just got individual spots where the first derivative was 0, here and there, at 0.5 and at x equals 2. So if I want to look at second derivative stuff, that all has different boundary values. So I'm going to change colors here. Let me do something greenish. So curvature-wise, this is curved upward from 0 to 1. And then curved downward from 1 to 2. So my second derivative is negative in this center section where I have this curved down section, and it's positive elsewhere other than at those 2 spots where the second derivative is 0. So if I want to talk about whereas, let's see, just in words, let me put this in black or something. If I want to talk, the function's values are positive all along. F values or G's values, whatever you want to call this, they're positive all along. But my first derivative is greater than 0. Let's see. From 0.5 to 2, so I'll use interval notation, open, because at 0.5 it's not positive. And then also again on the other side of 2 through, well, we're just using through 3 on a graph, but just looking at what I've got here, it's forever. So I've got this, oh wait, what was I looking at? I said less than 0, and I wrote the greater than 0. Sorry, apologize for that. Let me just change what I wrote. Eraser. Looking for, what am I writing? This is going (0.5 to 2, and then 2 onward. That's where f prime of x is positive. Sorry about that. No, I'm still trying to get to write. Draw. So my derivative is positive all along here. My first derivative is only negative in this first section, so I'll say negative infinity through 5. We only looked at parts of it, but this is actually the entire interesting part of the graph. So the only points between negative infinity and positive infinity that aren't mentioned in these 2 statements are the spots where the first derivative is equal to 0. F prime of x equals 0 at the individual spots x equals 0.5 and x equals 2, the boundaries. Now, if I wanted to talk about the second derivative, visually speaking, is about curvature. So let's see, I wrote positive. So where is it positive? Where this is curved up, the whole left side of the graph and this right side of the graph, not the middle section. So it's curved up on negative infinity through this point, which was at 1. And then again, union from 2 through infinity. It's curved downward, second derivative less than 0, in between there, 1 through 2. And the only other part that isn't mentioned where it says equal to 0 at, again, individual spots, those inflections, the places where it changes curvature at x equals 1 and x equals 2. So the y values, f values, are positive all along. The first derivative values, positive, negative, 0. The second derivative values were positive, negative, 0. Make sure you can explain those. But notice that we could do this all from the graph of just this function. So we used calculus to figure out where precisely these spots are. We found those values by just because I made this function so they came out at nice key points. But what we're going to talk about next time is how to locate those points from scratch as opposed to by luck filling in a table. But keep in mind, this would just be algebra. So we're not going to spend a lot of time on that. I will go through one where we go find the critical values, but that's what we have here, these critical values. We have critical values at x equals 0.5 and x equals 2. Those are the only two, if I'm looking to try to find maximum and minimum values, locally high and low points in a graph, these are the only two candidate spots. Because I can't have, I mean, other than endpoints, which I don't have endpoints on this, but just within the domain of this, those are the only points that are higher or lower than the points around them, supposedly. Now, this one turns out to be actually not of interest. It's just a flat spot. And we found that out by further analysis. But look in this graph, you can see this is the only local minimum we've got. This is, sometimes it's called a stationary point. Sometimes those are called stationary points too. People use that word in a variety of different ways, unfortunately. But this is a local minimum value, meaning it's lower than the points on either side of it. In other functions, there might be like, this turns around and comes back and goes down to negative infinity. That wouldn't make this not a local minimum anymore. But in context, it probably wouldn't be the solution we're looking for. Depends. This spot here is a local minimum. It's the only one we have in this graph. Even if I were to look all along, there's no little maximums, there's no tops of hills, notice. Unlike the sketch that I did at the beginning said, oh, maybe it looks kind of like that. There's no spots like that in this graph that are tops of hills. This one goes down and then up and doesn't fully change direction. It just pauses for a moment, goes horizontal without decreasing ever here. So that if we don't have an increase change to decrease, we're not going to have a local maximum. We did have a decrease change to increase, so we do have a local minimum. But in any case, these are our two critical values of the first derivative, and those help us locate all the candidate positions for maximums and minimums. Now, there was, remember that part of the definition, places where the derivative doesn't exist? Well, this is a polynomial. Its derivative exists everywhere because its derivative is also a polynomial. So other sorts of functions sometimes have non-existent derivatives at various spots, or their derivative doesn't have a value at a place where the function did, such as, like I said, absolute value graphs, even things like cube root. So if I have something like y equals x to the 1/3 power, if I look at its, this is defined on all real numbers. If I look at its derivative, thinking power rule, I get 1/3 x to the negative 2/3, which in radical notation is 1/3 times the cube root of x squared. While the original function is defined on all real numbers, this is undefined at x equals 0. So this being undefined at x equals 0 means the derivative, y prime, is undefined at the origin. Remember what cube root functions look like. I feel silly doing this because I'm in GC, but they look kind of like this F shape, but right at the origin, they don't disconnect, but it's that the slope is infinitely steep. It's a vertical tangent line at that spot. So there's not a value for the derivative, it doesn't end up being important. But in other cases, some sorts of weird fractional power graphs end up having a cusp like that, similar to the absolute value situation, where it is actually a lowest point, or if we're inverted, a highest point, without the function having any problems whatsoever, but the derivative is defined in a way where the derivative was positive and then negative, but instead of going through a spot where we can't define the value of that. All right, so I'm going to stop at that for today. I'm going to try to make sure that this was recording, but I kept getting messages. I don't know if they showed on your screen as well, that my internet connection was being unstable today. I hope that this recording goes through, and I will get it posted as soon as I can. All right, thank you, thank you.